Okay, this is lecture 17. Okay. So in the previous lecture we have considered drift diffusion simulator, and today I want to introduce Sharpeter command scheme for better numerical stability. So practically today's lecture is very important. So I wanted to start from the failure of our previous implementation. So previously I just show you that when we make a certain discretization of this function or this term, so this gradient of electrostatic potential can be well approximated as so difference of electrostatic potential divided by the distance between two neighboring nodes. And at that time I told you that okay, so here we have electron density, and since this electron density is more or less the value at the midpoint, so why don't you just apply linear approximation of electron density. That was our main motivation when we did our implementation. So now I hope that you can now have some values or simulation result, and if you do it correctly then you are able to calculate IB characteristics. But please have a look at this one. At the time I suggest you to use about 400 mesh point with 1 nanometer spacing. That was the recommended setting for your device structure. So now you have a sufficiently dense grid, and that was the result shown here. So here we have a position, this is X position, and here we have some another, this is N type, and here we have a P type. And now you can see, although it is a little bit difficult to see here, but here we have red line and blue line. There are two lines, and red line is the one obtained from our nonlinear Poisson equation. So although that is restricted to the equilibrium case, but as much as we are talking about the equilibrium condition, then this red line shows the correct result, so the reference result, and we wanted to fit our simulation result for drift diffusion simulation to that of a nonlinear Poisson equation. So this is the correct one, and our blue line should match to the red line. So when we have 1 nanometer spacing, please have a look at two curves. So how does it look like? So yes, although we have a small difference in this point, but it is not that much, so we can say that okay, it is acceptable. But this is related with 1 nanometer spacing. So here you have another extreme case. In this case we have introduced 10 nanometer spacing, so we have just 41 mesh points in this case, and please have a look at the result. So still, yes, even in this case our red line shows a beautiful result, and you can see that these are solutions of your simulation. Even when you do it correctly, you will get this result. So now you can ask me what happens in between these 2 points. For example, here, okay, let's wait for a while because our pencil is stopping. Okay, so You know that here we have some connecting lines between 2 points, and at this point it just dives deep into small electron density. What happens to this point? Actually, this one shows a regular value, and in between these 2 points, here we have another point, and at this point our electron density actually shows this negative value. So when we try to visualize it, then we must take logarithmic scale for this semi-log graph. So taking the log of negative number makes a certain error. So that's the reason why we have just disconnected lines here. It means that okay, with 10 nanometer spacing, we cannot get the correct positive electron density in our simulation. That is the situation we have currently. Okay, so maybe you think in this way. Okay, so 10 nanometer, in this case we have just spent 40 points, so this is seems to be a little bit low number, so maybe we can live with this 1 nanometer spacing forever. But please think about this case. This is just 1D, and if we go to even multi-dimensional cases like 2D or 3D, then it will make a certain complication. For example, let's say that here we have a 40, and let's say we have just 2 cube of 40. Okay, and here we have 400, and let's take a 400 cube of 400. Please make a comparison between these two numbers. What is the factor? So you can easily understand. In 3D case, we have a factor of 1000 between these two cases. So it means that once you say that okay, my simulation is just limited to 1 nanometer spacing, then your final three-dimensional structure will spend a lot of mesh points in order to have reasonable result. So this is not a very good situation, because we are always quite hungry for efficient simulation. So although we can solve a large system with spending quite a lot of computational resources, but still we always wanted to reduce the computational burden. Please note that the only difference between these two is just a number of grid points. So it is easy to understand, if we spend more grid, then our accuracy or solution, the accuracy of our solution can be improved. So this is a quite good and reasonable trend. Okay, if you pay more, then you will get more. So that is the situation. But point is, usually our situation is not located in this very lucky case, but many times we are somewhere around here. We wanted to reduce the number of mesh points as much as possible. So one good news is, okay, this is the result obtained from our naive implementation with taking the middle or average values of electron density or hole density for our implementation. So now we can improve this situation with Schappeter-Gummel scheme. One thing I wanted to say is, sometimes students ask me this question. Okay, here we have a negative electron density somewhere here, then is it related with a certain occurrence of same amount of hole density? Certainly it is not the case. Negative electron density is just nonsense, so you should not accept it. So once that happens, then your simulation, entire simulation is destroyed. So you should not allow the negative carrier density at all. Well, then what happens in reality? If you perform your device simulation, sometimes you have negative density, negative electron density, or hole density. Then what you have to do is during your Newton iteration, when you have negative carrier densities, then you just convert them into positive ones. So manually convert them into positive ones. So how can you do that? So there can be many different approaches, but anyway, it is certain that you should not consider negative carrier density as a temporal solution or intermediate solution of your solution procedure, because many times you have to take the log of your electron density or log of your hole density, and log of negative number is not defined properly, so it will just destroy your entire simulation. So it is very important to understand negative carrier density is just nonsense, so please do not allow it. So previously we have seen that 1 nanometer was acceptable and 10 nanometer was not acceptable. Then where can you find the boundary between acceptable or unacceptable? Or in other words, okay, that is to argue. So instead of that, say that when we have a negative electron density, what is the borderline between them? Here we have certain number, 5 nanometer. So 5 nanometer we have negative sign, negative electron density. 8 nanometer also, and when we come back, for example, 3 point some number, although we have errors obtained from our coarse graining, but still we have positive number. So we can say that around 5 nanometer, or here we have a 3 point something nanometer, somewhere here we have the occurrence of a negative electron density in this 10 to the 17 per cubic centimeter and 10 to the 17 per cubic centimeter example. Okay, so are you with me? So do you have any question? So up to now, what I have done is just to show you that although we did our best in our previous homework problem, but our implementation is not that good. So if we spend a lot of computational resources, then we can get reasonable results. But even at equilibrium, if we just relax the mesh condition, then yes, we have a certain problem. Okay. Also, up to now I have just shown you the result from 10 to the 17 per cubic centimeter, and how about the situation? So please have a look at this condition. It was the condition where we still have positive value. Okay, so that was the borderline, at the borderline of non-occurrence of negative electron density. Good. However, if we slightly increase the doping density or slightly increase the doping density, it shows that although we have the same delta x value, delta x is the same at every case, like 3.125 nanometer, but still just changing doping density generated some problems. Okay, it is just well, here we have still error but positive, and yes, this is just a failure of our numerical simulation. So we have a trend. Okay, if we have a dense grid, maybe it would be okay. However, also if we have high doping density, Na and Nd is high, then maybe we have to have even shorter distance between them. So simply speaking, if we have a further and further advanced device like 10 to the 20 per cubic centimeter or 10 to the 21 per cubic centimeter, then the requirement for mesh spacing becomes more strict, and so that will make significant burden on our mesh. So now you can understand this one. Up to now, I just shown you the equilibrium electron density, and in this symmetric structure, hole density shows exactly the same form with mirror image. So I don't want to describe hole density. Instead of that, let's go to our Ford IV characteristics. Ford IV characteristics means that I have applied a positive voltage to our anode node attached to the p-type region, and when you have a look at this one, this is number of intervals, means that this 100 is corresponding to 4 nanometer case, and this 800 is corresponding to delta x equal to half nanometer. So you can understand, well, this is a good one and this one is quite a bad one. And when you have a look at the current value, how does it look like? Here you have numbers exceeding 3.5 something. Of course, here we have quite a small number, but anyway, here we have 3.5. And when you have a look at the values with 4 nanometer spacing, can you read it? Well, I don't have an exact number, but it is still true that it is much smaller than 0.5. It seems that it's like just 0.1. So compared with this 3.5, beyond 3.5 at this point, it means that not only the electron density and hole density at equilibrium, but the solution at our meaningful IV characteristics is just becomes quite inaccurate by introducing this small number of grid points. Okay, if we go to other bias points like 0.7, then maybe this quality reduction is not that high. For example, here you can see that this value is 2.88, and here we have with 4 nanometer spacing, it is about 2.73 or something. Yes, so here we have still change like 15, and it is corresponding to for example 6.5 point or 6 point error in it. So this is still certain error. However, compared with this 0.1 volt case, the error becomes much smaller. Okay, so anyway, so it depends on the bias point. At some certain bias point, some problems occur, and at some bias conditions, it seems that it's okay. However, as a developer, our goal is to build a code which can work for general cases. So if your code works for certain bias and if your code does not work properly at another bias condition, then that is not a good program to be used by many users. So okay, now you understand. Well, already, although you have spent quite a lot of effort, but your implementation was not that good, so you wanted to now improve it. Finally, I wanted to discuss about this one. Then what is the root cause of this problem? So we have talked about two different reasons or factors. One was difference of neighboring points, and one was doping, and they can be merged into one single value potential difference between two nodes. So think about high doping density. If you have high doping density, then you can easily understand your, so this is, if this is position and if this is electron density, then you can see that this depletion region becomes nearly narrow. However, more or less when we have a certain change, so if we just draw potential, then there will be certain difference corresponding to the doping of our p-type region and n-type region. So now depletion region is significantly reduced. For example, it has some square root behavior. If you increase 100 times in your doping density, then it will shrink 10 times shorter depletion with, however, increase of your, how can I say, potential is not that high because it takes a logarithmic scale. So simply speaking, when we have this kind of thing and with the increased doping density, then now for if we have much more moderate transition here in previously with a relatively low doping density, but if we have a high doping density, now our transition becomes really sharp, and we can expect that the electric field in this depletion region can be increased significantly. So now you can understand this one. Previously we have talked about the case keeping the distance the same and only changing the doping density. It means that although we have the same setting, but in this PN junction we have a steep change of electrostatic potential. So that's the reason why we have higher difference of our electrostatic potential between two neighboring nodes. So please have a look at this one. These figures, here we have three figures, are obtained from three different delta x values. So when you have a look at this one, although the doping density is the same, so we are now looking at all the same result, but why do we have different values like just 0.01, 0.04, 0.05? The reason is we have just introduced more points and here we have less points. Simply speaking, it's like this. The potential changes, for example, schematically in this case. So in an extreme case, we just take 2 points. Then what is the potential difference? Of course, the potential difference will be the difference. However, if we introduce more points to describe the same system, then what is the difference between two nodes? So the potential difference between two nodes becomes much smaller than the previous case. So simply speaking, these three potential profiles always share the same potential profile physically. However, due to the difference of their real space spacing, so the value is somewhat reduced. So you can easily understand this 1 nanometer and 5 nanometer shows just approximately 5 times difference, and 1 nanometer and 4 nanometer case also shows about 4 nanometer difference. It is because the profile is given and only the spacing is reduced, so that's the reason why the potential difference is scaled accordingly. So now let's just have a look at these three graphs once again. What was the problem? Negative electron density. And my question was here, did we have negative electron density? No, it was just okay. How about 5 nanometer? At the time, we had negative electron density. So this one shows good result, and this one shows quite bad result, and this one shows just a borderline, at the borderline or on the borderline between good and bad case. And please have a look at this bad case. How does it look like? The peak potential difference between two neighboring nodes is approximately 50 millivolt. So that is the criteria. So please let me just read this statement. The maximum potential difference of 50 millivolt seems to be a threshold for the negative density. If we have the potential difference higher than 50 millivolt, so that makes some problems. So when you have 50 millivolts, then you must understand this is corresponding to just 2 times of our summer voltage. So now you must understand, in our discretization, somewhere in our discretization scheme, there will be the term corresponding to 2 times summer voltage, and that will be a trigger of a negative carrier density. Let's have a look at our problem. Okay. So that was the situation about can I say about 60 years ago. That was the situation we had. Our pioneers had such a situation, and there were 2 researchers whose name is Shapeter, family name, and Gummel, and they published a paper for a certain type of diode. So, and they published that paper for their analysis on this special type of diode, and in order to make such kind of a calculation, they invented a new scheme, new numerical scheme. So in their paper, actually this new scheme can be found not in the main body of their paper, but in the appendix of that paper. You can find a short description about their new scheme. Maybe they didn't think that this is a big contribution at the time, the contribution was just analysis on that special diode. However, it later it has found that actually this new numerical scheme can solve many previous difficulties of our drift diffusion simulation, so it became the standard. So currently we are now using this scheme. So if you wanted to see more story about that one, please have a look at your references, because there are tons of discussion about how good this scheme is. So let me just dive into the derivation. So simply speaking, in this model we are talking about just 1D. Question is, oh, we are now currently talking about 2D or 3-dimensional devices in our everyday research work. Then how can we restrict ourselves only to the 1D case? So it is not that difficult, because even when we have 2D, for example 2D case, then here we have the node and another node and another node and another node. Let's say if this is the case, then we can define edge connecting two nodes, and along this edge, each of them is called as edge and also edge, and this one-dimensional approximation can be applied to this edge current. So for example, in this 2D case, we calculate 5 edge current, and by properly make them sum with weighting factors, then we can calculate the current inside the control volume of this central node. So considering only 1D problem is just justified by this directional decomposition. So although we are considering 2D or 3D, but we just calculate the edge-wise carrier transport. Then the natural question is, it means that we do not calculate the electron transport along this direction, or at this point we do not calculate, yes, we don't calculate this kind of quantity. So the current conduction, which is perpendicular to the edge alignment, so we do not consider this kind of thing. So that's the reason why if we consider, for example, Maxwell equation, actually our treatment is not that suitable. So our treatment is good for our problem. So, and anyway, let's say that it is treated as a 1D case, then we can write down the expression for Jn. Jn is electron current density, can be obtained from the sum of drift term and diffusion term, and previously we just individually considered each term. Okay, the N was taken as average electron density, so it was taken as delta phi over delta x. And how about this dn over dx? Also, we just consider dn divided by dx. That was our previous implementation. However, the point is, as I told you before, this one, electron density is just averaged between i's point and I plus 1 point. Why this one is so bad approximation? So let me just show you this example. let's say here we have x and potential. Let's say here we have a point x sub I and another point x sub I plus 1, and happen to be here we have potential. Good, it is called as phi I, and happen to be we have another potential value phi I plus 1 at this point, and let's say that this straight line is the correct solution of our electrostatic potential. Let's say that this is real and this is real correct solution. Good. So if we take d phi over dx, then our assumption like a phi I plus 1 minus phi I xi plus 1 minus xi will be the exact answer. Good. But even under this special case, our previous attempt really fails. For example, now we wanted to calculate dn over dx. How does it look like? In this equilibrium case, then by taking the exponential of phi n, now we can find a certain n I value. Also, by taking the exponent of phi I plus 1, then we can find another value corresponding to n I plus 1. Then please try to draw your electron density at equilibrium. Does it look like this straight line? Actually not. You must have exponential growth of your electron density. So now you understand the shape of your electron density just looks like this. So if you have to calculate this dn over dx, then what is the required value? Can you take the value at this point, or that point, or the one at midpoint? This question is really difficult to be answered, because even in this case our electron density shows quite a rapid increase or sometimes a rapid decrease. So the slope itself becomes a function of a position even in this point. Okay, so anyway, the things like ni plus 1 minus ni divided by delta x cannot be a good approximation for our dn over dx terms, and also which is the correct n values which can be applied to our n, maybe midpoint value is not that appropriate. The point is, since this is really involved with exponential increase, if we take the real values at midpoint, then it would be much smaller than just midpoint value. So of course, this is related with the increase case, but if our electron density is now decreasing, then that will make also another situation. So simply speaking, now you understand, individually considering each term makes some problems. So Shapetta-Gumme scheme just makes quite a neat solution about this problem. Here, instead of assuming a form of electron density inside this edge or segment, the key idea is, well, anyway, the current density should be a constant. Wow. In this case, electron current density is a function of position. However, this assumption says that although it can be a function of a position, but actually it does not change. It is a constant. That is the real breakthrough applied in this case. So it means that in order to make this Jn, which can be a position dependent, as a constant, then our electron density should dynamically change to match this condition. So that is the main point. So here we still linear variation of electrostatic potential. Electrostatic potential changes linearly. However, electron density, which is exponential function of this phi, can change dynamically. That is our assumption. So now please have a look at this one. Although the last equation in this slide just the same form or same equation written in a little bit different form, but this form just stress that this is an equation or a differential equation for our electron density. Now we will treat this equation as a differential equation. So n is unknown variable, and this is a first order derivative, and this is a constant term, and this is a constant term. So sorry, this is not constant term, but this is a linear term, and first derivative and linear term and constant term. So it is really easy to solve this problem, because here we have a basis function which is exponentially changing, and of course we have two unknown coefficients, C1 and C2. However, C1 and C2 can be easily obtained from their boundary conditions. Okay, now it is given in this way, and just to insert this n values here and n values here to match values at xi node and x sub I plus 1 node, and I will just skip all kinds of solution procedure or derivation procedure, but although I'm skipping it for some certain easiness of our lecture, but all of you guys should follow this derivation at least once. So professor just showed it to me, yes, just believe him. This is not the right way to study this course. Please do it by yourself. You will find that it is not that straightforward, so sometimes you can be lost, so please try to do that. So anyway, by doing all kinds of these jobs, then you can find that okay, our C1 and C2, C1 coefficient can be written as n I plus 1 minus ni divided by certain quite a complicated function. And how about C2? our C2 coefficient is given as also quite complicated function. Why do we have this complication? Because our solution n has exponential dependence on the position. So in order to match ni and ni plus 1, our C1 and C2 should be very complicated. Anyway, so now we have C1 and C2, and we can now calculate Jn. Now we have the final form of J sub n. So maybe you feel a little bit uncomfortable with this form. We start from quite a neat form of electron density here. Well, we start from this form, but eventually our final result seems to be quite complicated. So let's have a look at once again. This is the form. Here we have a certain quantity Q, you know Q, and Dn. What is Dn? Dn is diffusivity, you know it. And delta X, this is xi plus 1 minus xi, you know it. Yes, they are just constants. Point is, now you have this term. Here you have electron density at x sub I plus 1, and here you have electron density at x sub I. It is true that our current density should be given as difference between these two electron densities, because even when we consider, for example, diffusion term, then how does it look like? Diffusion term is just given as a difference between Ni plus 1 and Ni. So it is easy to understand. But point is, in this Schapter-Gummel scheme, the coefficient for each term, Ni plus 1 and Ni, has complicated dependence on our potential, and only on potential. This is true. There is no further complication like dependence on Ni or Ni plus 1 or specific value of phi I or phi I plus 1. No, only the dependence or difference between phi I plus 1 and phi I is involved. So of course here we have exponential something, but anyway, this is a sole function of delta phi. So people make certain simplification or manipulation. So I will just show it later. But please make a comparison between our Schapter-Gummel scheme and our previous naive implementation. So this is the same electron current density, and sorry about that, I made mistakes. So upper one is taken from our naive implementation, and lower one is obtained from our new Schapter-Gummel scheme. So when you have a look at them, of course they share the constant values, but so that doesn't matter. And please have a look at these terms in parentheses. So in previous case, you can easily understand this one is corresponding to our diffusion term, and the second term is related with our drift term, and this difference is corresponding to electric field, related to the electric field, and this is corresponding to our average electron density. You can identify each term by term because we have made it such a way. However, when you have a look at the Shaped-Gummel scheme, where can you find the diffusion term? Or where can you find the drift term? So it is not that easy to find it. So what is B? This is B will be explained in next slide. But point is, in our previous implementation, we just separate drift and diffusion and treat them separately. However, in this case, they are just merged into one term and they are treated as a whole system. Okay, so now you can understand this one. But what is the function B? This function B is called as a Bernoulli function, and although it looks like something special, but it is simply written as this form: x divided by exponential x minus 1. That is simple. And now I'm just writing down or showing the B of x, Bernoulli function, and this is x. So this blue line is corresponding to the Bernoulli function. It has some special properties. For example, this Bernoulli function is always positive. For negative x, 0, or positive x, always this is positive. This is really important. So Bernoulli function shows always a positive value. And here we have something like a Bernoulli function at exactly 0 should be 1. But point is, it is not that easy to obtain from this implementation. For example, if you add 0 or insert 0 for x, then your upper part becomes just 0. And please, when you insert 0 here, your exponential function just gives unity and minus 1 gives 0. So it becomes 0 over 0. So simply speaking, when you just implement your Bernoulli function with this simple form, your Bernoulli function makes some problems at x equal to 0. So you need a special treatment for x equal to 0 case. So if your x is exactly 0, then you have to say that your Bernoulli function equal to 1. But point is, instead of this 0, let's say that your x is 10 to the minus 16, then what will happen? Even in this case, your numerical simulation makes some problems, because exponential x minus 1, when x is quite close to 0, then exponential x can be well approximated as 1 plus x and minus 1. It is given as x. Good. However, if you insert, for example, 10 to the minus 16, then what will happen? First of all, your exponential function, your computer program, first calculate exponential x. Then it will give you 1 plus 10 to the minus 16. But 1 plus 10 to the minus 16 is just treated as 1 in our user double precision number system. So your result will be just 1, and 1 minus 1 becomes exact 0. Although you must have 10 to the minus 16 as your calculation, but since it first takes exponential x and within given precision, so it will generate non-zero value 10 to the minus 16 is divided by exact number 0, so that will give you infinity number. So simply speaking, when you actually implement your Bernoulli function in your computer with given precision, please be careful around number 0. So not exactly 0, but around number 0 there can be a certain problem, so please be careful. So usually what we do is, okay, if absolute value of input variable x is small enough, then instead of using this original value, we just introduce Taylor expansion of this Bernoulli function. So with this Taylor expansion, we can avoid the problem of numerical difficulty, division by 0. Okay, so at positive extreme, then it is exponentially decay. Here we have exponential minus x term. Of course, here x term, but it doesn't contribute much. So we have exponential decay in this positive part. And if we go to the negative extreme, negative infinity, then it does not increase exponentially. It just behave like minus x. So this Bernoulli function has certain difference in its behavior when we go to positive infinity and negative infinity. So that is important. And it is monotonically decreasing, and when we take the gradient at 0, then you will find that this derivative has the slope of minus half. So okay, so the final remark is careful implementation is needed. So careful implementation is related with x close to 0. Of course, there is another case. Since this is related with the exponential function, for example, let's say that x equal to 10 to the 3 or 10 to the 6, then what will happen? If you take the exponential of 1000 or exponential over 1 million, then it will immediately give you infinity number, infinity minus 1. So that will also make some problems in your case. So simply speaking, if your input argument is far larger than certain number in positive direction, please treat it as just number 0 because it is rapidly decreasing. And if your input argument is far smaller than a certain sufficiently small negative number or sufficiently large negative number in absolute sense, then please treat it as minus x. So that's the reason why implementation of your Bernoulli function is quite tricky. And if you are interested, then please refer our previous conference presentation. So a few years ago, actually undergraduate student in our laboratory just to make a presentation in Korean conference on semiconductor on this subject. So please watch that video. That will be quite helpful. Anyway, so we should be careful about implementing it. So key is Taylor expansion. And of course, we need, since we are working with Newton-Raphson method, we need the derivative of this Bernoulli function. So here Bernoulli function means that dB over dx. We need this form too, and it can be well given as this form. Of course, you can try many different ways, but I just wanted to reuse Bernoulli function as much as possible, so you can make it in this way. So you can see that this is dB over dx, and although it looks like going up, but please note that this is 0. So always this dB over dx is always shows negative number, monotonically decreasing function. And of course it approaches to the asymptotic value of -1 when we have a negative x value, and if we go to positive x value, it approaches to just number 0. Okay, so this is the Bernoulli function. So compared with our previous lecture, so the burden, actual burden you must pay is implementation of a Bernoulli function and its derivative. It is required, newly required, to implement your Schapter-Gummel scheme. However, except for that, everything is just the same as before. So you can just reuse this Jacobian component. Yes, so you can do it. So it's not that difficult. And now I wanted to wrap up today's lecture with showing you the improved result. So the improvement is really significant. Actually, without the Schapter-Gummel scheme, we cannot solve many problems. For example, let's try to show you once again electron density at equilibrium. 41 mesh points means that we have now delta x equal to 10 nanometer, and this is our previous result. So you know that here we have a positive number, and here we have negative numbers and entire negative values. That was a drastic failure, was our previous implementation. And how about this? This is Schapter-Gummel scheme, and as you can see, the blue dots are obtained from our Schapter-Gummel scheme, and red line is corresponding to the nonlinear Poisson equation. How does it look like? They are showing almost exact agreement. It is because actually at equilibrium, Schapter-Gummel scheme can really reproduce nonlinear Poisson equation solution. So you can show it. So then what is this strange number? So this number is obtained from my own calculation. So starting from our previous non-linear Poisson equation solution, so this red curve, I just ran my new Schapter-Gummel scheme solver, and that was this 10 to the minus 14 was the update of potential phi in the unit of voltage. It means that the potential update is just 10 to the minus 14 volt. About 20 femtovolt difference is obtained in our new Schapter-Gummel scheme. So it means that virtually the solution is already given. So Shaped-Goldman scheme can recover nonlinear Poisson equation exactly. And how about the doping density? So we have used relatively relaxed value, and previously you have seen that, well, with 10 to the 17 it did not give us negative value. So let's just come back to our previous one. So here you can see that 4 times 10 to the 17 we have a negative, and just 10 to the 17 we have a positive values. And now we are looking at this 4 times 17 value, and when we have a look at our new scheme, this is 4 times 10 to the 17, so this one shows the result of our Shaped-Goldman scheme. So simply speaking, well, with this new Shaped-Goldman scheme, we can exactly recover the result of nonlinear Poisson equation. However, you can ask me this question. Okay, this has been shown, the equilibrium result, and how about non-equilibrium case, fold IV or reverse IV? So now you can see it clearly. So you remember that when we apply 0.1 volt with 4 nanometer spacing, the current almost vanishes. So that was really bad situation, although our solution is around somewhere around here, but we had quite a small value. But please have a look at this curve. This curve means that even with 4 nanometer spacing, you can find reasonably good value over your IV characteristics. How this can be possible? Because our electron density can be, even in this fold bias case, well calculated with this coarse grid. That's the reason why our current value is quite close to the one obtained from fine grid. So maybe you can ask me this question. It is very difficult to believe it. Just changing a little bit of our numerical discretization scheme, we have improved the quality of our solution drastically. How that can happen? What I wanted to say is this is really a rare case of our triumph. If you are involved with this numerical calculation, always you can try to improve your numerical scheme. So sometimes you make some success, or sometimes you have just a so-so result. But this Shaped-Goldman scheme shows the biggest achievement of previous work. So don't be overwhelmed by this achievement. So because this achievement obtained from very clever idea. What was the clever idea? In my opinion, this assumption, this requirement is the key. We wanted to have Jn as a constant, independent on the segment position. Once you apply this assumption, then the remaining thing, the calculation or manipulation, this can be done almost automatically. The important one is the idea to say, assertion that Jn should be constant over our interested segment. That is key assertion. So please note that when you do your own research work, important one is the key idea. Of course, the ability to perform proper manipulation or proper implementation is that is critically important, but without good enough idea to improve your previous problem, then it does not give you the best result. Okay, so now you can see that this can improve the Shaped-Gumel scheme, improve quite much the situation. So now you have a homework number 17. So I think that this is the pinnacle of our entire semester. Simply speaking, just to complete the developing your one-dimensional derivative diffusion solver with Shaped-Gumel scheme. So if you have not fully implemented your previous solver, then you have still time, 5 more days. Then please make your implementation. Also, Shaped-Gumel scheme and our previous naive scheme gives you good comparison data. So you have Shaped-Gumel scheme and our previous naive implementation, and even you have nonlinear Poisson equation. At equilibrium, all of your 3 implementation at reasonably fine grid should give you the correct result. So if your result does not show almost immediate solution at equilibrium, something is wrong. Especially in my opinion, you must concentrate on the relation between Shaped-Gumel scheme and nonlinear Poisson. So we can show that Shaped-Gumel scheme can reduce to nonlinear Poisson equation at equilibrium. So if you have some problems in your Shaped-Gumel scheme code, then please always try to check your solution with the solution of a nonlinear Poisson equation. If your residue makes some unreasonably high value, large values, when evaluated with the solution of a nonlinear Poisson equation, it means that your Jacobian or your residue function is completely wrong. So please try to fix your problem. Okay, so although we have lecture 17, but already we have finished the discussion about Shaped-Gumel scheme. Now we have 8 more lectures, and the final 2 will be made with recorded video, because I'm not here in these 2 last lectures, so I will just post my recorded video in the YouTube channel. And here we have 6 more offline lectures. So for these 6 more remaining lectures, I will try to give you as much as possible as new development items in order to introduce more simulation capabilities. But in my opinion, today's homework is the most important one in our entire semester. You should be able to write down your own derivative diffusion solver. Okay, so that is critically important. So please concentrate on this problem. Okay, if you don't have any question, then I would like to wrap up today's lecture. Thank you for your attention.